Greetings and welcome to lecture number 14 of the course Introduction to Fourier Analysis. On the previous lecture we established the Fourier inversion formula for Schwarz functions and a bit more generally for L1 functions whose Fourier transform is also an L1 function. In this case f of x equals, for Lebesgue almost every x in Rd, the integral over Rd of f hat xi times e to the power 2 pi I xi dot x d xi. On this lecture, we will use the Fourier inversion theorem to develop the L2 theory of the Fourier transform. Recall that the main goal of these lectures is to define the weak Fourier transform of any LP function f, when the exponent p is between 1 and infinity. More precisely, we would like the weak Fourier transform to be a function f hat, which satisfies the duality formula, namely that the integral of f times hat phi equals the integral of f hat times phi for all suitable test functions phi. As we have already discussed, the space of suitable test functions here is the space of Schwarz functions. Therefore, the main remaining question is, if f is a function in LP, then does there exist a function f hat such that the duality formula makes sense and is valid for all Schwarz functions? And if such a function f hat exists, then what can we say about its properties? On this lecture, we answer these questions in the case when p equals 2. If f is an L2 function, we will associate to f another uniquely determined L2 function f hat such that the duality formula holds for all Schwarz functions. In this endeavor, the key role is played by the following Corollary 3.13 of the Fourier inversion theorem. The two formulas in this corollary are known as the Parseval and Plancherel formulas. Let phi and psi be Schwarz functions. Then, first, the integral of phi times the complex conjugate of psi equals the integral of the Fourier transform of phi times the complex conjugate of the Fourier transform of psi. Second, as a corollary, the L2 norm of phi equals the L2 norm of the Fourier transform of phi. The proof of Theorem 3.13 is based on the Fourier inversion and duality formulas for Schwarz functions. The first observation is that the Fourier inversion formula implies the following relation. For any Schwarz function phi and for any vector x in Rd, phi of x equals the Fourier transform of the Fourier transform of phi evaluated at minus x. This is not hard to see. For a change, let's start with the right-hand side of the equation. The Fourier transform of the Fourier transform of phi at minus x equals, by definition, the integral of the Fourier transform of phi at xi times e to the power 2 pi I xi dot x d xi. But this integral expression is precisely the one which appears in the Fourier inversion formula. Therefore, since phi was assumed to be a Schwarz function, the expression equals phi at x as claimed. With this formula in hand, we start modifying the left-hand side of the Parseval formula, namely the integral of phi x times the complex conjugate of psi x dx. The first step is simply to plug in the formula we obtained just above. In the second step, we make a change of variables from x to minus y. This way, we end up with the integral of double hat phi at y times the complex conjugate of psi at minus y dy. Next, we apply the duality formula to move one of the hats above phi to become a hat above psi. But, to do this precisely, we need to record that the Fourier transform of the function y maps to the complex conjugate of psi at minus y, evaluated at xi, equals the complex conjugate of the Fourier transform of psi evaluated at xi. The justification of this formula is another straightforward computation. Starting from the left-hand side, we have an integral of the complex conjugate of psi at minus y times e to the power minus 2 pi I xi dot y dy. We first make a change of variables which changes the sign of y, and we end up with the integral of the complex conjugate of psi at y times e to the power 2 pi I xi dot y dy. Then we pull the complex conjugate outside the integral. In other words, the previous integral equals the complex conjugate of the integral of psi y times e to the power minus 2 pi I xi dot y dy. But this final expression is precisely the right-hand side we were after, namely the complex conjugate of the Fourier transform of psi evaluated at xi. We then return to the application of the duality formula. Using the duality formula, combined with the equation we just established, we have that the integral of double hat at y times the complex conjugate of psi at minus y dy equals the integral of hat phi at xi times the complex conjugate of hat psi at xi dxi. But this is already the correct right-hand side of the Parseval identity, and hence the proof of the Parseval identity is complete. The Plancherel identity is an immediate corollary of the Parseval identity applied to the case where phi equals psi. Namely, the L2 norm of phi squared equals the integral of the absolute value of phi squared, which further equals the integral of phi times the complex conjugate of phi. At this step, we apply the Parseval identity, and then, taking the same steps in the reverse order, we end up with the L2 norm of the Fourier transform of phi squared, as desired. This completes the proof of the Plancherel identity and also the proof of Corollary 3.13. We are then almost prepared to define the Fourier transform of L2 functions. One more technical tool is needed. This is proposition 3.14, which is often known as the bounded linear extension theorem. Let X be a normed space and let Y be a Banach space, that is, a complete normed space. In the application, you may think that both X and Y are the space L2. Then let X0 be a dense subset of X, and let T0 be a bounded linear map which is defined on X0 and takes values in Y. The words bounded linear map mean that there exists a positive constant C such that the norm of T0 at X is bounded from above by C times the norm of X for any vector X in X0. You have probably encountered the definition of bounded linear maps before, but let me still remind you that the linear map between normed spaces is bounded if and only if it is continuous. So we could have equally well said that T0 is a continuous linear map between X0 and Y. Then the conclusion of the theorem is that there exists a unique extension of T0 to a linear map T defined on the whole space X. In other words, there exists a unique bounded linear map T defined on X and taking values in Y, such that the restriction of T to X0 coincides with T0. Moreover, the operator T is bounded by the same constant C as T0. For every X in X, the norm of Tx is bounded by C times the norm of X. The bounded linear extension theorem might look long and complicated, but actually the proof is quite straightforward. We leave it as an exercise. As we already mentioned, the spaces X and Y to which the extension theorem will be applied are both equal to L2. And of course, the dense subset X0 is the space of Schwarz functions. We observe that by the Plancherel identity, the Fourier transform is a bounded linear map on the space of Schwarz functions viewed as a subspace of L2. In fact, the Fourier transform map is an isometry on this dense subspace of L2. Therefore, by the bounded linear extension theorem, there exists a unique bounded extension to the whole space L2, denoted by calligraphic F. This extension calligraphic F gives the definition of the Fourier transform for all L2 functions, which is definition 3.15. Namely, if f is an L2 function, we define its Fourier transform to be the image of f under the extended operator calligraphic F. It is often a little cumbersome to keep using the notation calligraphic F, so in the sequel, the Fourier transform for an L2 function will also be denoted by hat f. But if f is an L2 function, it is important to keep in mind that hat f is not necessarily given by the pointwise formula hat of xi equals the integral of fx times e to the power minus 2 pi I xi.x dx. Indeed, if f is not an L1 function, this integral is not absolutely convergent. The L2 Fourier transform defined just above is also a weak Fourier transform in the sense that the duality formula is valid. In fact, proposition 3.16 contains an even stronger statement. Let f and g be L2 functions. then the integral of f times the L2 Fourier transform of g equals the integral of the L2 Fourier transform of f times g. Since all the functions f, g, hat f and hat g are L2 functions, all of these integrals are absolutely convergent by the Cauchy-Schwarz inequality. We leave the proof of proposition 3.16 as an exercise. As a hint, use the definition of the L2 Fourier transform and the fact that the formula holds for Schwarz functions. By essentially the same argument, one can also show that the Parseval identity extends from Schwarz functions to L2 functions. Namely, if f and g are L2 functions, then the integral of f times the complex conjugate of g equals the integral of the L2 Fourier transform of f times the complex conjugate of the L2 Fourier transform of g. We also leave this proof as an exercise, otherwise we would completely spoil the previous exercise. Recall that the Fourier transform is invertible on the space of Schwarz functions. We next show that the same property extends to the space L2. This is the content of Theorem 3.17. If g is an L2 function, then there exists an L2 function f such that the L2 Fourier transform of f equals g. Naturally, this equation between hat f and g now means that hat f and g agree as elements of L2, that is, Lebesgue almost everywhere. To prove Theorem 3.17, fix an L2 function g. Using the density of the Schwarz functions in L2, choose a sequence psi j of Schwarz functions which converge to g in the L2 norm. Any converging sequence is a Cauchy sequence, so in particular the functions psi j form a Cauchy sequence in L2. Next, we apply the invertibility of the Fourier transform on the space of Schwarz functions. For every function psi j, we pick another Schwarz function phi j whose Fourier transform agrees with psi j. This Fourier transform refers to the basic pointwise Fourier transform. The Fourier inversion formula even gives an explicit expression for phi j, namely phi j equals the tilde version of the Fourier transform of psi j. Next, we observe that also the sequence phi j forms a Cauchy sequence in L2. This follows immediately from the Plancherel identity. The L2 norm of the difference phi I minus phi j equals the L2 norm of hat phi I minus hat phi j. And the functions phi j were chosen so that their Fourier transforms equal psi j. Since the functions psi j form a Cauchy sequence in L2, as we observed earlier, this identity shows that the same also holds for the functions phi j. Now we are almost done. Since the space L2 is a Banach space, the Cauchy sequence of the functions phi j converges to some function f in L2. It remains to check that the L2 Fourier transform of this function f equals g. First, recall that the L2 Fourier transform of f is, by definition, the image of f under the abstract linear map calligraphic f, which extends the pointwise Fourier transform map on the space of Schwarz functions to the space L2. One of the basic properties of the operator calligraphic f was its boundedness on L2. Since the functions phi j converge to f, the limit of the images calligraphic f of phi j equals calligraphic f of the function f. Of course, this limit here is a limit in the L2 sense. Next, recall that the functions phi j were chosen so that their pointwise Fourier transform equals psi j. Moreover, the operator calligraphic f coincides with the pointwise Fourier transform on the Schwarz space. So, calligraphic f of phi j equals psi j. Finally, the L2 limit of the functions psi j was g. This is how the sequence psi j was chosen. Now we have shown that the L2 Fourier transform of f equals g, and this completes the proof of Theorem 3.17. This also completes the basic L2 theory of the Fourier transform. Let us quickly summarize what we have just learned. The Fourier transform can be defined on the space L2 in such a way that the Fourier transform map is an invertible linear isometry on L2. Moreover, this definition coincides with the pointwise definition on the dense subspace of Schwarz functions. Finally, the L2 Fourier transform is also a weak Fourier transform. And the Parseval identity holds for all L2 functions f and g. This might be a good place to end the lecture, but there is a short topic remaining on these lecture notes, which I wish to finish before moving on to the next bigger issue, which will be the definition of the Fourier transform on general LP spaces and even beyond. This short topic concerns the injectivity of the Fourier transform, which we already used during the proof of Theorem 3.7a. Namely, if f is an L1 function whose Fourier transform vanishes, then f also vanishes. We will prove this in a moment. There is another question of similar flavor, which we will also address here. Namely, if f is a function in both L1 and L2, then we have two alternative definitions for the Fourier transform available, and it is important to verify that these two definitions coincide. Both of these questions will be resolved by a generally useful result in Theorem 3.18, which has nothing to do with the Fourier transform. It says that if f is a locally integrable function on Rd, and the integral of f times any test function vanishes, then f equals 0 Lebesgue almost everywhere. Here we recall that the space calligraphic D of test functions consists of smooth and compactly supported functions. So, in particular, the integral in the theorem is well defined because f was assumed to be locally integrable, and the support of the function phi is compact. To prove Theorem 3.18, it evidently suffices to show that f multiplied with an arbitrary test function psi equals 0 almost everywhere. Indeed, if f does not vanish identically, then it is easy to choose a test function psi that also the product f times psi does not vanish identically. Multiplying f by psi has the benefit that the product is now an L1 function and not just a locally integrable function. We denote this product by big F. We then observe that big F satisfies the same hypothesis as small f. If phi is an arbitrary test function, then the integral of big F times phi equals the integral of the product f times phi psi. And since phi psi is again a test function, this integral vanishes by the initial assumption. Thus, we have upgraded the L1 log assumption of little f to an L1 assumption of big F without violating the main hypothesis. To show that big F vanishes Lebesgue almost everywhere, let phi delta be an approximate identity which consists of test functions. Such approximate identities exist, and we have even mentioned an explicit construction after definition 1.10. This was when we first discussed approximate identities in connection with Fourier series. Now, since big F is an L1 function, the convolutions of big F with the functions phi delta converge to big F in the L1 norm as delta tends to 0. This was part of lemma 3.11. Let us spell out what the convolution means. The convolution of f with phi delta at x equals the integral of fy times phi delta of x minus y dy. But this integral is the integral of big F times a certain test function. So the integral vanishes by our assumption. Therefore, big F is approximated in the L1 norm by the function 0. It follows that big F is the 0 element of L1, which implies that big F vanishes Lebesgue almost everywhere. This is what we claimed, and the proof of Theorem 3.18 is complete. The injectivity and consistency results we mentioned earlier are now easy corollaries. We start with Corollary 3.19, which says that if the Fourier transform of an L1 function f vanishes, then f itself is 0 almost everywhere. To prove this, we start by using the duality formula. If phi is any Schwarz function, then the integral of f times hat phi equals the integral of hat f times phi. And since hat f is assumed to be 0, this integral is also 0. Second, we recall from the Fourier inversion theorem for Schwarz functions that any Schwarz function is the Fourier transform of another Schwarz function. So, if the integral of f times the Fourier transform of any Schwarz function vanishes, as we have just seen, then also the integral of f times any Schwarz function vanishes. But Schwarz functions contain the test functions, so now it follows immediately from the previous result, Theorem 3.18, that f is 0 Lebesgue almost everywhere. This completes the proof of Corollary 3.19. Finally, we settled the consistency question between the L1 and L2 Fourier transforms in a situation where they are both well defined. And this is the content of Corollary 3.20. Let f be a function in both L1 and L2. Then the L2 Fourier transform of f, denoted by calligraphic f of f, coincides for Lebesgue almost every xi with the L1 Fourier transform of f at xi. This is, as usual, defined as the integral over Rd of fx times e to the power minus 2 by I xi.x dx. To prove this corollary, let hat f be the L1 Fourier transform of f, and let calligraphic f of f be the L2 Fourier transform of f. As we have seen, both hat f and calligraphic f of f are weak Fourier transforms. In other words, if phi is a Schwarz function, then the integral of f times hat phi equals either the integral of hat f times phi or the integral of calligraphic f of f times phi. For the L1 Fourier transform, this follows from the duality formula. For the L2 Fourier transform, we recorded this in proposition 3.16, whose proof was left as an exercise. Now we can subtract these two equations from each other. The result is that the integral of hat f minus calligraphic f of f times any Schwarz function phi is equal to 0. But the difference here, hat f minus calligraphic f of f, is certainly a locally integrable function. In fact, it is a difference between an L infinity function and an L2 function. So it follows from Theorem 3.18 that this difference is 0 Lebesgue almost surely. In other words, hat f equals calligraphic f of f almost everywhere, as we claimed. This completes the proof of Corollary 3.20. This also concludes lecture number 14 on the course Introduction to Fourier Analysis. Goodbye.